Hello students. In the previous class we have learnt the valence shell electron pair repulsion theory and the arrangement of the electron pairs, that is geometry and shape without a lone pair of electrons on the central atom, and we will be continuing the same valence shell electron pair repulsion theory where the central atom has one or more lone pairs of electrons. We have the molecule type here, that is Ab2E, and this 2 is nothing but the number of bonding pairs, and this E represents a number of lone pairs, that is one lone pair. If you add this 2 and 1, it becomes just Ab3. If it was Ab3, we would have written the geometry in this manner: A, B and another B here. But since there is one lone pair, so in the place of this B we are writing here one bond and one lone pair, right? So when we say arrangement of electron pairs, it includes lone pair as well as bond pair, right? And the geometry is trigonal planar. When we say with respect to shape, we have to hide this lone pair, right? And when we hide this lone pair, we have to concentrate on this part now, so that becomes shape which is bent. And the examples for such a type of molecules where the shape is bent, one is SO2, other one is ozone, that is O3. The second molecule type is of AB3E, which means the central atom A is having 3 bond pairs and one E, that is lone pair. One lone pair and bonding pairs are 3. And if you see, we are having the central atom, and if I write all in terms of bond pair, all in terms of bond pair, okay, now this becomes a tetrahedral. But one lone pair is present, and if I write that lone pair here, okay, this is one lone pair and this is another lone pair, you can see that arrangement of electron pairs, that is nothing but geometry we are dealing here, right? So geometry is a tetrahedral, okay, but in the place of one of the bond pair we are having here one lone pair, due to which the shape now we speak is we have to hide this part and we have to concentrate only on this part, right? In such case the shape is called as trigonal pyramidal. Trigonal pyramidal. And the examples, if you see, we are having the best example, that is ammonia molecule, right? We already know that ammonia, we have learned the hybridization of ammonia where nitrogen atom is sp3 hybridization, and if you see the orbital diagram, we are having here one lone pair in one of the sp3 hybridized orbital, and the remaining are involved in bonding with the hydrogen atom, right? Actually, if the tetrahedral was there, the bond angle would have been 109 degree 28 minutes, right? But since the presence of one lone pair makes it interaction, that is this bond pair and this lone pair are interacting, that is repulsion is taking place, due to which the bond angle is reduced to 107 degrees. Now the next molecule type you can see here, it is of Ab2E2. A is the central atom, B is the atom which is surrounding A. How many are there? By 2, and those are forming by bond pairs, that is number of bonding pairs. And E2, you can see here E2, these are representing number of lone pairs. How many are there? 2 are there, right? Now, arrangement of electron pairs, which is giving us geometry. Central atom is A. It is surrounded by two lone pairs. So there is one lone pair and there is another lone pair, and two bonding pairs. Actually, this is also just like tetrahedron only. This is 1, 2, 3 and 4. Okay, if you join this, we will get a tetrahedral only, and that is the reason we have mentioned here tetrahedral geometry. But because of the presence of these lone pairs, the shape is going to change, and that change is nothing but called as distortion, right? So these lone pairs, if I consider this in the form of what orbitals here, okay, these are going to interact. Lone pair and lone pair are more interacting when compared with lone pair and bond pair, right? Here also they are going to interact here, that is lone pair and bond pair, due to which the angle from 109 degree 28 minutes, which was in tetrahedral, and because of the presence of these two lone pairs, okay, so you can see here this is 1 and this is 2, this is 1 and this is 2, because of the presence of these two lone pairs, the bond angle here it is 104.5 degrees, and when it is 104.5 degrees, the molecule undergoes distortion to have a shape, and that shape is called as bent shape. And the best example is water molecule. You already learned the hybridization of water molecule. Central atom is oxygen here, and we know that it is having two lone pairs, okay, and one is involved in hydrogen and other the sp3 hybridized orbital is involved in water, one s orbital of hydrogen. And because of this presence of lone pairs of electrons, this angle, okay, so the tetrahedral angle in the case of water molecule will be reduced to 104.5 degrees. Now, the next molecule, type is AB4E. Number of bonding pairs, there are 4 bonding pairs which are surrounded to the central atom A, and E is representing a number of lone pairs, that is 1. Arrangement of electron pairs gives us geometry, right? Now suppose if I have taken here AB5 without the lone pairs, then I would have taken an example of PCl5, phosphorus pentachloride. Phosphorus pentachloride has the hybridization of sp3d, and we have already learned the geometry of PCl5 having sp3d hybridization is trigonal bipyramidal, pyramidal without lone pairs, right? So here we are having one lone pair in this case, which is the type of molecule AB4E, and when you see the geometry which is representing of arrangement of electron pair including both bonding as well as non-bonding, right? So you can see here 4 atoms are surrounding to the central atom A, and one is occupied by what? Lone pair, right? And if I join this, this becomes triangular in nature, right? This becomes what? Triangular in nature, right? And one we are having axial bond above, other one is axial bond what? Below. So if I have to consider this lone pair as one bond, then it would have been what? Trigonal pyramidal. So here also it is trigonal pyramidal. Why? Because we are learning the geometry with inclusion of bond pairs as well as lone pairs, right? But because of the presence of one lone pair, the shape of the molecule will undergo distortion, and it is called as seesaw, right? Now this lone pair which is present here, okay, I will call it as it has occupied equatorial position. Question might be present that why the lone pairs are not present here, okay? If it was present here, it would undergo repulsion between this and this bonding. So therefore, in order to avoid less repulsion, the lone pairs are occupying the equatorial position here, right? And when you see the shape, it is seesaw. You can see the diagram here. Now it was in this manner, okay. Here it was different, okay. Lone pair were occupying here, right? And if you see here, the lone pairs are present here now, right? So if it is present here, we can write this manner. Now these are all, these three bonds are what, in equatorial. This is above and this is what, below. And if you see here, okay, in terms of what, systematized geometry, sulfur atom is present at the center, because we are dealing with now example, which is that example SF4. Sulfur is present at the center, right? This is one fluorine atom, this is another fluorine atom, right? And here we would have got what, our lone pairs, right? So therefore this fluorine and this fluorine, you can see that the shape of the molecule is just like what, a seesaw. Is it clear, students? So whenever you come across SF4, sulfur tetrafluoride, remember that it is having 4 bond pairs and 1 lone pairs. Arrangement of electron pairs, that is geometry, is a trigonal bipyramidal, but the shape will be seesaw shape. In the next example, the molecule type is AB3E2. Central atom is A, it is surrounded by 3 atoms, B, and 2 lone pairs. So number of bonding pairs are 3, number of lone pairs are 2, and the arrangement of electron pairs, including bonding electrons and lone pair of electrons, is called as geometry here, right? And the geometry is, you can see here, trigonal bipyramidal. Why? Because 3 plus 2 is nothing but 5 only, right? So we have learned with example PCl5, central atom is A and the surrounding atoms are what, B. How many times? 5 times. And the geometry is trigonal bipyramidal, PYRAMIDAL, right? But the only difference is that here it is AB3, it means 3 are bond pairs and the remaining 2 are what, lone pairs, right? And here also trigonal, can you see that? So this becomes the triangular part here, right? So therefore here there is, this position is occupied 1 atom B. The equatorial positions are here occupied by what, lone pairs, and the other 2 B atoms, one is above, other one is below, right? So the geometry, as I've told you, it includes lone pair of electrons as well as bonding electrons. So the geometry is trigonal bipyramidal. But when it comes to with respect to shape, we have to recall that we have to close the lone pairs. We have to close the lone pairs. That means we have to keep one paper or thumb on this water lone pairs. Under such condition, the shape will become what? Can you see now? This is nothing but what? T shape. This is nothing but what? T shape, right? And a best example for the molecule of the type AB3E2 is ClF3. Is it clear, students? Now we will have the last 2 examples, right? And here we are going to discuss with respect to the molecule type, which is of AB5E. Central atom is A, surrounded by 5 B atoms, and there is 1 E, which means what? 1 lone pair and 5 bond pairs, right? If suppose it was AB6, I would have taken the best example with respect to SF6. Already we have learned the hybridization of this SF6. Actually it was sp3d2, right? Is it clear, students? We have learned that. And the shape of this would have been octahedral, that is SF6. But here of this 6 atoms, now the number of bonding pairs are 5 and 1 is lone pair, right? Arrangement of the electron pairs, which is nothing but geometry, which includes a lone pair as well as bond pair, right? So 5 plus 1 is 6. So therefore 6 is the number with respect to what are the B atoms in case of SF6, but in the case of here AB5E, one of the position is occupied by lone pair and the remaining 5 are represented here, right? So these four occupy at the four corners of the square. One will be present above and the other one will be present below, that is a lone pair, right? And because of the presence of lone pair, the shape of the molecule is distorted, and that shape is nothing but called as a square pyramid. And as I have told you, when it comes to what the shape, we are supposed to what close the lone pair. If I close the lone pair with the help of paper or with the help of the thumb, then the remaining part is this part, okay, and this part is nothing but square pyramid. I hope you are able to follow this. This is nothing but what a square pyramid. Is it clear, students? And the example for the type of the molecule AB5E, that is 5 bond pair and 1 lone pair, it is boron, not boron, BrF5. And similarly, if the molecule type is AB4, if the molecule type is AB4E2, it means there are 4 bond pairs and 2 lone pairs. Of course, 4 and 2 when we add it is 6 only, right? Of these 4 bond pairs which are present here, that is when I speak with arrangement of electron pairs, which is nothing but geometry, right? The 4 bond pairs are present towards the 4 corners of the square here, right? And the 2 lone pairs are present above. So you can see here one lone pair above the plane and the other one below the plane, right? And the shape is octahedral. No doubt in the earlier example also it was octahedral only, right? But because of the presence of these 2 lone pairs, one above and one below, the shape is undergoing distortion. And when I speak with respect to that shape, as I've already told you, that I have to hide the lone pairs. If I hide this lone pair and this lone pair, the remaining part is nothing but the bond pair, and that is nothing but the square planar, and that becomes square planar. Is it clear, students? And the example for square planar type of molecules which are having AB4E2 type is XeF4. Now, table 4.8 in our NCERT textbook, page number 112, explains the reason for the distortion, that is a change or alteration or altered from its original shape, that is in the geometry of the molecule, right? So let us have some couple of examples. The molecule type is of AB2E, which reveals there are number of bond pairs. Here you can see there are 4 bond pairs, okay, but here it has been mentioned as what a B2. B is, if you see the example here, it is with respect to sulfur dioxide, SO2, right? But the bond pairs in case of SO2, if you see the central atom is S, B it has been told as a 2, but in case of SO2 we are having what 2 oxygen, that is 2, but here there is double bond, student. So here there is what a double bond. In a VSEPR theory postulates, we have already learned one postulate: whenever there is a double bond, we have to treat it as what a single bond only. That we have to what remember. But here we have to write the number of bonding pairs. Bonding pairs are 4. Can you see, this is one bond, this is second bond, this is third bond, this is fourth bond. While representing the structure, we have to write what number of bonding pairs as what it is only. But atoms are what, this is divalent here, that we have to what remember. And number of lone pairs, we are having what, one lone pair, okay. You can see that lone pair is present here. On the central atom we have to concentrate, but not on the oxygen atoms, because in oxygen atoms also we are having what lone pairs, but we are not supposed to what count these lone pairs which are present on what oxygen atoms, right? And you can see now, see here, sulfur has 6 valence electrons, right? And each of the oxygen has 6 valence electron, right? So there are 2 oxygen atoms and together they are having what 12 valence electrons. So altogether in SO2 there are 18 valence electrons. There are 18 valence electrons. And if you see those 18 valence electrons, okay, just I want to say that I will be writing here once again 18 valence electrons, sulfur, oxygen, and here oxygen, right? So 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. I hope you're understanding, students. So 18 valence electrons. By using this, we have written the Lewis dot structure, and if you go for what the octet configuration, we can find that what each of the atom in the case of SO2 is having what octet configurations, right? And now let us come with respect to the arrangement of electron. When it comes to arrangement of electrons, we have already learned that we have to include the lone pair as well as what a bond pair, lone pair as well as bond pair. So these lone pair of electrons, if I draw one orbital here, these are present in what this orbital, right? And because of this orbital which is containing a lone pair, so distortion is happening. That is a change with respect to their geometry, okay? And when it is undergoing change in the geometry, we call the shape of the molecule, and that shape in case of SO2 is what? Bent here. Is it clear, students? So here the angle, if you see AB2E, okay, AB2E, if I just speak of AB3 without a lone pair, the bond angle would have been 120 degrees. The bond angle would have been 120 degrees. Let us find out the reason for this shape acquired. Theoretically, the shape should have been triangular planar. Theoretically, the shape should have been triangular planar with a bond angle of 120 degree, but actually it is found to be bent shape. I hope you can see this is bent shape, or simply called as what a V-shaped molecule. The reason being the lone pair and bond pair repulsion. The reason is lone pair and bond pair. So this is the lone pair, right? And this is the bond pair. Okay, here also what a bond pair, right? The reason being is lone pair bond pair repulsion is much more as compared to the bond pair and bond pair repulsion. So this is the bond pair and this is the bond pair. So this repulsion, when you consider, is less when you compare with that of what the lone pair and the bond pair. So here the repulsion is more. So the angle is reduced to 109.5 degrees from 120 degrees. So conclude, so if at all if it is concluded, students, the presence of lone pair of electrons makes the geometry of the molecule to undergo distortion, and that what we call it as a shape, and it will be having what the different shapes depending upon the number of lone pair of electrons. Is it clear, students? Now let us have the another example. So molecule type, you can see here it is AB3, right? Number of bonding pairs we are having 3, and number of lone pairs, that is what 1. And when we speak of arrangement of electron, we have to include this bond pairs as well as what lone pairs, right? And the best example for AB3E type of molecule, we are having ammonia molecule, that is NH3 with 1 lone pair. You can see that the lone pair is present on this nitrogen atom, and nitrogen atom is of sp3 hybridization. So the three hydrogen atoms including the lone pair will be occupying the four corners of tetrahedron. Okay, so this is one lobe which is having a lone pair, and this orbital is sp3 orbital. One is here and the remaining are here. Now if you see this is the tetrahedral nature of the water ammonia molecule. But because of the presence of one lone pair, the shape of ammonia molecule is not a tetrahedral, it will undergo distortion, and when it undergoes a distortion, the shape is called as a trigonal pyramidal, or simply what a pyramidal in nature. Is it clear, students? Now if you see the reason for the shape acquired, which is that shape trigonal pyramidal. If there had been a bond pair in the place of lone pair. See the sentence, if there had been a bond pair in the place of lone pair, right? So if this was a bond, right, in the place of lone pair, the shape would have been tetrahedral. We know that if there are 4 bonds surrounding the central atom, 4 bond pairs, then the shape would have been tetrahedral. But one lone pair is present, and due to the repulsion between lone pair and bond pair, see that repulsion between lone pair and bond pair. So this is the lone pair, you can see in this diagram here, this is the lone pair and this is the bond pair. Okay, it will undergo repulsion here as well as here. Okay, and that is called as a lone pair, because we know that these are lone pair and these are bond pair, right? So the repulsion between lone pair and bond pair, which is more than bond pair and bond pair. Now this is bond pair, okay, and this is bond pair. So repulsion between this bond pair and bond pair is less, if at all, if it is compared with the repulsion between lone pair and bond pair, right? So therefore the angle between the bond pairs is reduced to 107 degrees from the normal tetrahedral angle, that is 109.5 degrees. Now let us take another example where there is a distortion in the molecule because of the presence of lone pair of electrons. Molecule type, you can see it is AB2E2. It means the central atom A is surrounded by 2 atoms which are B, and there are 2 lone pairs of electrons. So bonding pairs are 2, number of lone pairs are 2. When we speak of arrangement of electrons, we have to include these both, which are those bond pairs as well as what lone pairs. And the typical example is water molecule, right? If you see water molecule here, the central atom oxygen is of sp3 hybridization. sp3 means 1s and 3p, totally will be what 4 orbitals which are nothing but sp3, right? In this 4 sp3 orbitals, 2 orbitals will be having a lone pair of electrons, because we have learned their number of lone pairs, how many are there? 2 are there. So therefore, so the 2 lone pairs, so this is one lone pair and this is the another lone pair, okay, and this is sp3 and even this also is sp3. Central atom is O, that is oxygen. 2 sp3 are having the 2 lone pairs, and the remaining sp3 and this sp3 will be overlapping with 1s1 atomic orbital of a hydrogen atom to form water molecule, right? And when I speak of arrangement of electron, as I've already told you, we have to include the lone pair as well as water bond pair, right? And because of the presence of these lone pairs, because of the presence of these lone pairs, the shape of the molecule is undergoing a change, and that change is nothing but here it is bent here, okay? And if you see the reason for the shape acquired, right, the shape should have been tetrahedral if there were all bond pairs, okay? If there were all bond pair means there was no presence of lone pair. At that time we could have written like this, okay? So oxygen, so these are the 4 the valencies, okay, or I cannot say valency because oxygen is divalent. If there were the lone pairs that were substituted by bond pairs, then it would have been a tetrahedral, right? But the 2 lone pairs are present, so the shape is distorted tetrahedral. See the technical word how it is described, the shape is distorted tetrahedral, or it is also called as angular, or it is also called as bent shape, right? And the reason is lone pair repulsion is more. See this is students, okay? So this repulsion, what is that? Lone pair and lone pair repulsion is more than that of bond pair and bond pair repulsion. So this is the bond and this is the bond. The repulsion between bond pair and bond pair is less when compared with that of what the lone pair and lone pair. Thus the angle is reduced to 104.5 degrees from the normal tetrahedral angle, that is 109.5 degrees. Now let us have another example of the type of the type AB4E, and here the number of bonding pairs are 4 and the number of lone pairs are 1, right? And if I speak of arrangement of electrons, I have to include these 4 bonding pairs as well as 1 lone pair, right? And the example what we can see when we are having the molecule of the type AB4E is SF4, right? The central atom S, which you can see here, it is present as S, and the 4 fluorine atoms, okay, you can represent here, right? In any direction you first represent it and you keep 1 lone pair, okay? Is it clear? And now you can concentrate that the 3 fluorine atoms, okay, the 3 fluorine atoms, I will change the color so that it becomes much clear now, right? These 3 fluorine atoms are present in one triangle, right? And this lone pair, I will draw one bond and I will represent in this manner. Fine. Now these fluorine atoms are occupying equatorial positions. This is axial position. One of the fluorine is present in axial position, right? And one lone pair is also present in axial position. If it is present in this manner, then this lone pair will be interacting with this bond pair, okay? Similarly this equatorial bond will also be interacting with this lone pair, and the same holds true for this fluorine atom to interact with this lone pair, because we know that there is a repulsion between lone pair and bond pair more when we compared with that of a bond pair and bond pair, right? Is it clear? And because of the presence of this lone pair, the shape will be seesaw. The shape will be what? A seesaw, right? And as I've told you here, there is interaction. So this lone pair is interacting with this bond, similarly here also and similarly here also. It means that the lone pair has to be present in other than axial position, so that there are less repulsion, okay? So you can see here this is more stable. Now the lone pair is present in equatorial. Earlier it was present in axial. Now the lone pair is present in equatorial position, and the sulfur atoms, 2 sulfur atoms are also present in equatorial position, and the remaining 2 sulfur atoms, one is above, other one is below. By being so, the lone pair, by being so in equatorial position, there is less interaction. It will interact with only this fluorine atom and that of this fluorine atom. Only 2 are there. But in case of earlier, there were 3 interactions. For that is the reason the lone pair in the molecule SF4, it will be occupying at equatorial position, and because of the presence of lone pair, the shape is called as seesaw. And you can see this molecular geometry here, seesaw type of what representation, right? So this is the triangular here, this is equatorial positions. Again these 2 are equatorial, this is above and this is what? Below. And the seesaw, whenever it is a seesaw, you have to recall that the best example is SF4. Now let us try to understand the reason for the shape acquired in A, okay? So this A is here now, okay? This A is here. The lone pair is present at axial position, so there are 3 lone pair bond pair repulsion at 90 degree, as we have already understood just now. But whereas in the case of diagram B, that B is, where is that B? That B is underneath here, it is below this diagram, okay? So below this diagram here, that is nothing but B here, okay? So in B, the lone pair is in equatorial position. Already I have told you just now, okay? Equatorial position. So this is equatorial position, and there are 2 lone pair bond pair repulsion. Hence the arrangement B is more stable, and the shape shown in the B is described as distorted tetrahedron. It is described as a distorted tetrahedron. Tetrahedron means there are 4 bond pairs and 1 extra lone pair is present, means it means that it is a distorted tetrahedron, or it is also called as a folded square, or it is also called as seesaw shape. Is it clear, students? So the last example with respect to the lone pairs in which the shape is changing, that is a distortion is going on. Okay, let us try to understand that example. The example is AB3. The example is AB3E2. It means central atom A is surrounded by 3 atoms which are by means of bonding pairs, and there are 2 lone pairs, right? So 3 plus 2 is what, of 5. So arrangement of electrons will include both, that is bond pairs as well as lone pairs, right? So there are 3 types of representation, A, B and C. Okay, we can represent. So how to represent means, you can recall that the lone pairs must always be at equatorial positions. Remember this point, students. The lone pair of electrons must always be in equatorial position, so as to reduce the repulsion between the bond pair and the lone pair, right? So in the first example, it has been mentioned here. Okay, you can see this is one fluorine halogen bond, this is another fluorine chlorine bond, and this is the third fluorine chlorine bond. Okay, the example is ClF3, okay, which is having a 2 lone pair of electrons. You don't worry about how this lone pairs and bond pairs are there. Okay, we are going to learn in competitive, and I'll bring one easy trick for you to remember how the lone pairs can be calculated and how the bond pairs can be calculated, right? So if you see now, this fluorine atom is above and this is below. It means these fluorine atoms are on axial position. One of the fluorine atom is present in equatorial, and this one lone pair, I will draw one orbital here. Okay, now here these are present in 2 different orbitals. Okay, the same thing has extrapolated here. If you see now, this is above and this is what, below, right? It means the lone pair can interact with this axial bond above, and this lone pair can interact with this axial bond below. Only 2 interactions are there, right? If you see in the case of B or that of what, C, right? What you can see that here in the case of C, the lone pairs are in axial position, above as well as what, below. So when it is present above, it is going to interact with this equatorial bond, with this equatorial bond, along with this equatorial bond. Similarly, the lone pair which is present below, that will also interact with these 3 axial bonds. So therefore we can see that there are 6 interactions with the lone pair and that of bond pair. So therefore, in order to minimize the repulsions, the lone pair of electrons in ClF3, they will be occupying the equatorial positions, right? And due to which the shape is now called as T shape. As I have already told you, whenever it comes to shape, you have to close the lone pairs. If I close this lone pair, with the help of thumb or with the help of paper, the remaining part you can see only this part, that is called as T shape. And if you see the reason for the shape acquired here, right? In A, the lone pair are at equatorial positions, so there are less bond pair repulsion as compared to the other structures, which are those B and that of C, in which the lone pairs are at axial positions, right? So the most stable structure, that is A, is preferred, which is having a T shape. Is it clear, students? Even you can see here this diagram which has been mentioned here. Okay, that is what, 2 lone pairs, and that is nothing but T shape. Okay, so this is the orbital having lone pairs at equatorial, right? And when it comes to shape, I have told you that just close this lone pair with the help of this thumb or what, paper, right? So the remaining part is just nothing but called as T shape. Is it clear, students? And now we have to conclude this valence shell electron pair repulsion theory. So valence shell electron pair repulsion theory is able to predict the geometry of a large number of molecules, especially the compounds of p block elements, more accurately. It is also quite useful in determining the geometry quite accurately, even when the energy difference between the possible structures is very small. That is because of presence of lone pair of electrons, right? The theoretical basis of valence shell electron pair repulsion theory regarding the effects of electron pair repulsions on molecular shapes is not that much clear. So far we have learned so many examples and all, but still yet we say that it is not that much of clear, and it continues to be a subject of doubt and what discussion. These are the things that you have to what recall, students, right? And to conclude, we will have the last slide in where we can see the clear representation. Okay, now you can just go through. So here in this diagram, the valence shell electron pair repulsion theories, all the molecules with the lone pair of electrons on central atom, without the lone pair of electrons on central atom has been what mentioned. Okay, all you have to do is just carefully go through. So here in the first one, okay, here I'll call it as 1, and this is called as linear. Okay, and you can see I have written the example here AX2, and we know that if it is linear means bond angle will be, bond angle is 180, and the hybridization is sp, right? So this is first. So I'll come back to here second one, okay, which is that molecule that is AX3 or AB3, okay, whichever you take, that is left for you. The shape is a trigonal planar, right? And the bond angle is 120 degree, right? If this one of the x in the case of AX3, one of the x in the case of AX3, if it is occupied by one lone pair, if it is occupied by one lone pair, then it becomes A, B, 2 and E. Okay, here it has been given as AX2E. Okay, you can write it as AB2E also. Then the shape is bent or angular. Is it clear, students? Now when it comes to what 3 here, okay, that is tetrahedral. Okay, tetrahedral AB4 type, AB4 type. Okay, the bond angle is 109 degree 28 minutes, right? Now if one of the bonded atom is replaced by one lone pair, then the shape is called as trigonal pyramidal, and I have told you that example is NH3, which is having one lone pair. If it was tetrahedral, then I would have given it as what, a CH4, right? Is it clear, students? Now if this AX4, whatever it has been represented here, AX4, if the bonding electrons are replaced by two lone pairs, okay, you can see here two lone pairs, if these are present, then the shape would be what, a bent or angular. Here I want to give the example of water molecule, right? In case of water molecule, there are two lone pair of electrons, and the shape of the molecule is bent, and the bond angle is less than 109 degrees, or more precisely you can call it as 104.5 degrees. So in case of water it is 104.5 degrees, and in the case of ammonia, that is AX3, okay, in the case of ammonia the bond angle is 107 degrees, right? Let us come back to this fourth one here. Fourth one, AX5. So AX5 I can write it as AB5, and the best example is PCl5, and the shape is trigonal bipyramidal, and the hybridization is sp3d. Okay, so this is AX5 or AB5. But in this, if one of the bond pairs is occupied by one lone pair, then it becomes a seesaw shape. Okay, then it becomes what, a seesaw shape. That you have to what remember, students. If the one lone pair which was occupied here, if I make another lone pair, two lone pairs are there, then it becomes a T shape. Then it becomes a T shape, right? And this is the example with respect to competitive, okay, which is not included in our NCRT. This was not included in our NCRT, but it can be taken for competitive, right? If AX5 of this there are two bond pairs and there are three lone pairs, then the shape will again become linear. Okay, can you see this? This is nothing but what, a linear here, right? And the last one, that is with respect to number 5 here, octahedral AX6. Okay, that would have been called as AB5, or we can call it as not 5, it is AB6, or it can be called as SF6. Shape would have been, geometry would have been octahedral. But if there is one lone pair, then it is called as a square pyramidal, and if there are two lone pairs, then it is called as a square planar in nature. Is it clear, students? Thank you for watching, and we will be concluding this class now, and in the next class we are coming with competitive questions.